Alright, so in this video, I'm going to be explaining another important paper with the title Dynamically Rewired Message Passing with Delay. This paper in 2023. Message passing neural networks have been shown to suffer from the phenomenon of over-squashing that causes poor performance for tasks relying on long-range interaction. This can be largely attributed to message passing only occurring locally over a node's immediate neighbors. Rewiring approaches attempting to make graphs more connected and supposedly better suited to long-range tasks often lose the inductive bias provided by distance on the graph, since they make distance nodes communicate instantly at every layer. So we propose a framework applicable to any message passing neural network that performs a layer-dependent rewiring to ensure gradual densification of the graph. We also propose a delay mechanism that permits skip connections between nodes depending on the layer and their mutual distance. We validate our approach on several long-range tasks and show that it outperforms graph transformers and multi-hop message passing neural networks. So we drew a new framework for aggregating information over distant nodes that goes beyond the limitations of classical message passing neural network. So we have a K-hop neighborhood. And the K-hop of a node I represents the nodes at distance exactly K, a subset of the nodes that can be reached by a walk of length K. So this is a message passing neural network class that every time we have aggregation and update. And we have talked about over-squashing problem and over-smoothing problem. So what is the idea of this paper? We introduce a framework to handle the aggregation of messages. We discuss how message passing neural network present a static way of collecting messages at each layer, which is ultimately responsible for over-squashing. By removing such static inductive bias, we unlock a physics-inspired way of message passing neural network to exchange information that is more suited to handle long-range interactions. So consider two nodes I and J at distance R. So there is a distance R, and in a classical message passing, these two nodes start interacting at layer R. So this holds. So because the aggregation at each layer is computed using the same graph, one can bound such interaction with powers of adjacency. So we have two problems. Distant nodes can only communicate by exchanging information with their neighbors, and distant nodes always interact with a fixed delay given by their distance. So we can say that in a message passing neural network, two nodes at distance R always interact with the latency or delay of exactly R. And R, a to the power of R, our transition matrix to the power of R, can be an upper bound for that. So that was the idea. Now they want to do a dynamic rewiring. We start by addressing the limitations, and we define the update in dynamically rewired Drew message passing neural network. So AGG equal to I, this reduces to classical message passing neural network. So if your aggregation is I, then it's classical message. But second, unlike augmented message passing neural network, the sets over which we compute aggregation differ depending on the layer. with the hop and sub k of I only being added from the case layer. So while this framework shares similarities with other multi-hop message passing neural network, it features a novel mechanism, dynamic rewiring of the graph at each layer to include aggregation from each k hop within distance L+1. So this is the delay mechanism. We generalize it to also account for whether nodes should interact with fixed, if any, delay. So currently, we have two opposing scenarios. In message passing neural network, nodes interact with the constant delay given by their distance, leading to the same lack of information. Nodes interact only from certain depths of architecture, but without any delay. For Drew, two nodes at distant R communicate directly after R layers. Since information has now been able to travel from J to I, but what if we consider the state of J as it was when the information left to flow towards I? We account for an extra degree of freedom tau, representing the delay of messages exchanged among nodes at distant R. So if delay is 0, then the nodes at distant k interact with the case layer without delay. So we formalize it by introducing our delay to be this maximum. And then they talk about instances of their framework, that how it is related to the architectures that we know. Then they define Drew gated GCN version of that, and this is how we do gating. This is element-wise product, and we do this because k-neighborhood weight sharing achieves comparably strong results with non-weight sharing. So we can see it as a distance-aware skip connections. We choose a source node, which is colored blue, on which to focus and demonstrate information flow from this node at each layer. We use arrows to denote direction of information transfer and specify hop connection distance. But in the classical message passing neural network, at every layer, information only travels from a node to its immediate neighbors. But in Drew, the graph changes based on the layer, with newly added edges connecting nodes at distant R from layer R-1. So all of these helps us to mitigate over squashing. Also, it can be good for local smoothing to avoid over smoothing. And these are benchmarks for long-range graph. We use peptide function, and these two especially, peptide struct and peptide function. So they compare it with the benchmark like graph convolution, gated graph convolution, even with the transformer and lab PE. They compare it and they see some improvement.